Hello everyone and welcome back to another video. So today we're going to be solving the LeetCode question 295, find median from a data stream. Alright, so the median is the middle value in an ordered integer list. If the size of the list is even, there is going to be no middle value. So the median is the mean of the two middle values. Cool, so in this case we're going to have a class called median finder. And so what we have to do is at each point we're going to have, using the add nums method, we're going to have numbers added to this object. And at any point, they could ask us to find the median of all the numbers we have so far. So let's say first we have the number 2, then 3, and then 4 added. And then they ask us to find the median. Then in that case, the median is going to be the value 3. So let's see how we can actually solve this question. So let's say we have this data stream. So first we're given the number 1, and then 2, and then so on and so forth. So let's actually first come up with a brute force or a simple solution for this. So first, let's say we get the number 1. We have a list with the number 1. Then let's say we get the number 2 as well. So then we have 1 and 2. Now let's say we get the number 0. So that's 1, 2, 0. So if at any point now I ask you to find the median, it's not going to be that simple, right? So what we could do is whenever I'm asked to find the median, what I could do is I could first sort this value. So the numbers I have are 1 to 0. I could sort it, which would give me 0, 1, 2, and look at whatever the middle index is, which in this case, it's 1. So in this case, the median is 1. Now, this is a method I could do. Now, in the worst case, to sort, it's going to take me n log n. And let's say I have to find the median after each insertion. So the worst case is going to be n times n log n for this method. Now, what is a simpler method we could do with the similar time complexity? So what I could do is, instead of just blindly appending a value, I could place the value at the correct position. So in this case, I got the value 0. So instead of just appending it to the ending, I could add it to where it belongs. So essentially, it's going to work like an insertion sort. Now, the worst case for this is that all of the values get appended or inserted at the ending when it's in ascending order, right? So even this method over here, so now the next value is -1, so I put that in its correct position. So this method is going to have a time complexity. So the worst case is we have to go all the way to the ending, and we got to do this at each time step. So that is nothing else but big O n squared, okay? So now this is a solution that would work, and if at any point they ask us to find the median, we go to the middle elements, in this case 0 and 1, and its average is going to be 1 by 2, which is 0.5. So these two are going to be our brute force solution. So one of them is sorting whenever we need to, and the other is using insertion sort so that our array is always sorted. Now, let's try to look for a solution which actually improves both of these time complexities. Now, to do this, there's a very unique solution, and to kind of point it out, let me first write the numbers in ascending order. Okay, perfect. So these are the same numbers, but I just wrote them in ascending order. So now let's say I want to find the median of these values. Now, what is that going to be? Well, in this case, how many numbers do I have? I have 1, 2, 3, 4, 5, 6, 7. 7 numbers, and the fourth index in this case, the third index in this case is the number 2. So that is going to be our median. So the median is 2. So what I want to do is I want to take the same ascending order of list and kind of divide it into different parts. So essentially we have one part over here, which is the median itself, which I'll call M. And to the right of it, we have all the values that are greater than the median, okay? And to the left of it, we have all of the values that are less than or equal to the median. Now, we could have just had greater than or equal to on the right and only less than on the left. Either would work, okay? So let's just say I am assuming this. I will just call this the left-hand side, and let's call this the right-hand side. So essentially what I'm trying to do is I'm trying to break this question down into a smaller part, which is essentially that we have a median, and we have all of the values that are less than or equal to median, and all of the values that are greater than the median. Now, a very simple observation that we can make is that the median is going to be in between the maximum value of the left-hand side, which is 1, and the minimum value of the right-hand side, which is 3, right? So we can kind of use this answer or observation to find what the median is. So in this case, it's 2. And whatever the median is has to be in between the greatest value of the left and the smallest value of the right. So this is going to be our basic idea of breaking it down into three different parts, and we'll see how we can actually use this to find the median. So now before that, one simple thing is how can we actually, what data structure can we use to keep track of this? So a very simple thing we could use is a heap. So a heap is going to allow us to keep the maximum value at the root for the left-hand side, and simultaneously we can keep track of the minimum value of the root at the root for the right-hand side, okay? And essentially when we have the maximum value of the left and the minimum of the right, it'll be easy for us to find out where the median is going to lie, okay? So that being said, let's actually see how this is going to work out with the step-by-step example. And the example that I have over here should go over all of the edge cases as well. So let's take a look at that. Cool, so to start off, I'm just gonna initialize the left-hand part. So this is going to be a heap. Now again, we want the maximum value, so this is going to be a max heap, okay? Then we're also going to initialize the right-hand side, and over here we want the minimum value, so this is going to be a min heap. And finally, we're also going to keep track of the median value, okay? So one more thing that we're actually going to keep track of is the size of the number of elements on each of the left and right-hand sides, okay? So in the beginning, they're both going to have a size of 0. Just to make it a bit more easier to understand, I just want to go through a simple example first. So let's say we have these values 0, 1, and 2. So in this case, what would actually end up happening is these values would be part of the left-hand side, and the value 2 would be part of the right-hand side. Now, that is one possibility, and another possibility we could have is we could have just the number 0 on the left-hand side, and we could have the numbers 1 and 2 on the right-hand side, okay? So in this case, the left and right are going to deviate by size by 1, okay? And what is the median going to be? So in this case, over here, right has two values, which is 1 and 2, and left has 0. And in this case, left has 0 and 1, and right has 2. So this is how I want you to think about it. So in this case, since they both deviate by size by exactly 1, whatever side has more elements, its root element is going to be the median. So in this case, so for the left, we're keeping track of a max heap, and the right is a min heap, right? So on the left-hand side, we have 0 and 1. So what is the root going to be? The root is 1. That is going to be our median. So now let's look at the bottom example as well. So in this case, we have more elements on the right-hand side, and the minimum value is 1. So the median, again, is going to be 1. So this is going to be the basic idea we're going to be using. But now, if at any time, so let's say we have something like 0, 1, 2, 3, 4, right? So now let's say only 0 is part of the left element, and everything else is part of right. This is never going to give us a correct answer. There are too many elements on the right. We want the left and right elements, the number of elements, to be as balanced as possible, right? We want the difference to be at most 1. If it is anything more than that, there's no point of using this method to find the median, because we're doing this based on the assumption that the left consists of all the elements less than or equal to the median, and the right is everything greater than the median, okay? So again, one last example. So now let's say we have an even number of elements, 0, 1, 2, and 3. Now the median is going to be the average of 1 and 2. So over here, what is going to happen is, what we want to happen, at least ideally, is we want this to encompass the left elements, 0 and 1, and the right elements to be 2 and 3, okay? So now in this case, they both have the same number of elements, okay? Left has 2, right has 2. If at any point the left and right heaps have the same number of elements, what that is basically telling us is that we have an even number of elements. So now in this case, we have 0 and 1, and we have 2 and 3. So what we do is we take the root of both of them. So in this case, what is the root going to be? It's a max heap, so it's going to be 1. And the root of 2 and 3, it's a min heap, so it's going to be 2. So we take 1 plus 2 and take its average, and that is equal to 1.5. So if at any time the sizes of the left and right are same, we take the roots of both of the heaps and find its average as our solution, okay? So if that doesn't make sense, it should make a lot more sense. But if it does make sense, I think that's more than enough to kind of come up with the solution by yourself. Cool. Okay, so in the beginning, we're going to assume the median to be 0. Okay. And now the first value we get in our data stream is 1. So 1 is greater than the median. So we place it over here. So we place 1 over there. Perfect. So now, so just to make it simple for you, I will also write the numbers in ascending order over here. So we have the number 1. So what is the median going to be? So like I said, they have different sizes. Well, this has a size of 1. So, and they deviate by at most 1 again. So over here, we take its root. So the root of it is 1. Cool. So now we have the number 2. 2 is greater than the median, so we add it to the right. So now we add 2. Is it still a min heap? It is still a min heap, so that's good. So now over here, the size deviates more than 1. It deviates by 2. So in this case, we want to keep it as balanced as possible. So how can we do that? What element do we push to the left-hand side? 1 or 2? Well, that is pretty obvious. Since this is a min heap, we're going to take the smallest element and put it on the left-hand side. Because remember, left is everything smaller, right? So in this case, we pop out the 1, okay? And we're going to add it to the left-hand side. So, and then we add the 2 to the right-hand side. So this is what we currently have. And by doing this, the size is going to be balanced. The size of both of them is going to be 1. Perfect. And the elements we have are 1 and 2. So what is a median in this case? Now, since the sizes are the same, we take the roots of both of them, which is 1 plus 2, and find the average, right? So 1 plus 2 by 2, which is 3 by 2, 1.5. Perfect. So let's keep going on and see how this looks like. So now we have 0. 0 is less than the median, so we add it over here. Is this a max heap? It is. So now we can continue, and it has a size of 2. So, and 0 would be over here. Cool. So it deviates by at most 1, so this is fine for us. And in this case, what are we going to get? So the median is going to be the 1. So, okay. So we have more elements on the left, so we take its root, which is 1. So the median is 1. Perfect. Okay, so now we have negative 1. Okay, so it would look something like this. Now, negative 1 is less than the median. Now, if we do that, we would have a size of 3 on the left. So we have to balance it out. Now, in this case, we had to move something to the right. Now, what number do we move to the right? Again, right is everything greater than the median. So we take the largest value and move it to the right. So that is nothing else but the number 1. Okay, so number 1, so 1 comes over here. Okay, now one thing we have to make sure of is when we add this 1, it is not a min heap anymore, right? So we have to swap them. Okay, I'll do that. Just give me a second. And after doing that, we have to also add the new number, which is negative 1. Okay, so we add negative 1. So we had the 0 as root and negative 1 on the left. So this is a max heap, but we have to fix this. So let's just swap the two numbers. So 1 is here and 2 is here. Cool. So now this is a min heap as well. Okay. So now in this case, we take both of its roots, 0 and 1, and we find the median because the size is both the same. This has a size of 2 as well. So that is 0 plus 1 by 2, which is 0.5. That is the median. Perfect. Now we have the number 5. 5 is greater than 0.5. So we add it over here. Is it still a min heap? It is. The size deviates by at most 1. So what is the median? Well, the median is going to be this root, which is 1. Cool. So the median is 1, and you can look over here. It still makes sense. Okay. So now we have to add the number 3. 3 is greater than the median, so we add it over here. Is this still a min heap? It is. But now the size deviates too much, so we do the same thing again. So we were at 3. So first we have to move one of the elements to the left. So that is going to be 1. Okay, so let's pop out the 1. So the 1 comes over here. And now we have to maintain this as a max heap. So we can just swap these two numbers. 1 is going to be here. 0 is going to be here. Cool. So we've swapped. Okay, so now this has a size of 3. Okay, cool. Now we have to make sure we add the value 3 over here. So we had 2 and 5. So the value on the usually, so let's just keep the 5 up top over here. And we have 2. Now we have to add the number 3. So this is not a min heap. So what's going to happen is the 3 comes here, and then we have 5 over here. But in this case, 2 is smaller, so we swap that as well. So 2 over here, 3 over here. So now this is a min heap over here. So now they have the same size. What is the number we added? We added 3. So this is what we end up with. And the median is going to be the average of 1 and 2. In other words, the roots of both sides. So 1 and 2's average is going to be 1 plus 2 by 2, which is nothing else but 3 by 2, which is 1.5. Cool. So we have a median of 1.5 right now. Okay, so now finally we have the last number, which is 4. 4 is greater than the median, so we're going to add it over here. Is it still a min heap? Well, it is, so that is fine. And now we have to find the median again. So let me just update this as well. So the median right now, there are more elements on the right-hand side. So we take its root, which is 2. And if you want to look at all of these values, the median in this case is the 2, right? And it is exactly what I said. There is going to be a deviation of at most 1 in the case when we have odd numbers. So in this case, we have 2, 3, 4 on the right-hand side. And that extra element on either side, wherever it is, that extra element is the median, which in this case is 2. Now, if they were equal, let's say we had negative 2 here, then in that case, we take the average of the 2 roots, which is 1 and 2 in this case. Okay, so in this case, we return 2 as the median for this at this point, and this is exactly how we're going to do this. So now let's see what this looks like in code. Alright, so we're going to start off by first initializing a few things. So we're going to have the left max heap and the right min heap, and we're going to initialize our median to 0. Now we're going to have our add num method. Okay, so over here what we're going to do is we're going to check if the number is less than or equal to our median. Okay, so if this is the case over here, the number should be added to the left max heap. Okay, so if this is not the case, then in that case the number should be added to the right min heap. Okay, so this is essentially going to be the entire logic of this. Now inside of each of these if and else statements, we're going to have another piece of logic, which is essentially if the number of elements in the left heap is less than the number of elements in the right heap, if it's less than or equal to, then in that case we can add another element. Now let's say the number of elements in the left heap is greater than the number of elements in the right heap. Well, what that means is that we have to remove one of the elements from the left heap, take it to the right heap, and then append the new element to the left heap. And we're doing that just to balance the two sides. So I'll just show you what that looks like for one of them, and then we'll just kind of replicate that for the second one. Now, another small thing I forgot to mention is we are going to be using heapq for this implementation. So if you don't know what that is, it is an inbuilt Python library that we can use to kind of implement heaps. And essentially one thing that you should note is that heapq is only able to do minimum heaps, okay? So how do you do a max heap using heapq? Well, that's pretty simple. All you do is you insert the negative values. So having a negative values inserted to a min heap is as good as looking at it as a max heap when you pop it out and take its negative, okay? So that is how we're going to be getting a max heap out of it. Okay, cool. So over here, we're first going to check the length of our left heap, and we're going to compare that with the length of our right heap. Okay, so self right min heap. Okay, so essentially the left heap has to be less than or equal to the length of the right heap. Now, if this is the case, then we can just directly push the element to over here, right? We can push it directly to the left heap. So this is going to be, where are we going to push it? Well, we're going to push it to the left max heap. And now in this case, we want to keep track of a max heap. So we're going to push the negative number, okay? Now, if this is not the case, what does that mean? Well, that means that there are more elements on the left heap. So we have to remove one of those elements, take it to the right heap, and then push this number, okay? So first we're going to first pop that number out, okay? So where are we popping it from? Well, we're going to be popping it from the left max heap, okay? Now what we're going to do is we're going to push this to the right, okay? So we're going to push it to the right min heap. So self dot right min heap. And we're going to push the negative of the top. or you could just over here you could just do negative. Either of them should work. Okay. Now finally we have to push the current number to the left heap. So let's just copy this up. And where are we pushing it? Instead of the right heap, we're going to push it to the left heap. And again, we're going to push the negative of the number because we're keeping track of a max heap. So we're going to do the similar thing on the for pushing a value to the right min heap. So let's just do that quickly as well. So over here, I'll just copy it and just change the values accordingly. Okay. So over here, we're going to check if the right min heap so the right min heap has to be less than or equal to the left max heap. So let's just do that. And if that is true, then in that case, we're going to push the number to the right min heap. And in this case, it's not going to be the negative number because it is a min heap. Okay. So if that is not the case, we have to move an element from the right heap to the left heap, then push the number to the right heap. So in this case, we're going to pop this element out from the right min heap, and then we're going to push it to the left max heap, okay? So we're going to push it to the left max heap, and we're going to push the negative of it, because again, it's a max heap. And now over here, we're going to push the current number to the right min heap, and we're just going to push the number, not the negative of it. Okay, so cool, we got the adding number part done, but one thing we didn't do is we have to also update our median at each time step. So to do that, what I'm going to do is I'm going to have a update median count. Now the reason we want to update it at each and every time step is because each time when we get a new number, we're making this comparison with the median, okay? So let's just make a method called update median, okay? And let's define it over here. So let's just do it right over here. So def update median self. We're not going to be returning anything. We'll just be updating it. Okay, so the condition for this is going to be pretty straightforward. So at each time, we have two conditions to check. So first, we check the lengths of them. And if the lengths are both the same, then we pop out both of the values and find its average. And over here, we're just directly going to update our median. Okay, so we take the top value, the root of the left max heap, okay, and we add that with the root of the right min heap, okay, and we'll just make sure we're taking the floating point values, okay, and we're going to add both of these up, and then we're going to divide it by 2.0, right? We're finding the average. Cool. So one small thing that we have to note for this is when we're taking the left max heap, remember we have to take the negative value of that, okay? So that should be it. Cool. So now we have two more conditions. So another condition is, let's just copy it. So let's say when we have more values, the length of the left heap is greater. So then in that case, all we do is, I'll just copy this over here. So then we just pop out the value from the left heap, and that is all we care about. And finally, we have the last condition, which is when we have more values in the right heap. So then in that case, we're just going to update it with the root of the right heap, okay? So we'll just do self.median, and it's equal to this over here. Cool. And finally, we got to define the find median value. So each step, we're calling the update median, and we're updating it. And if at any point someone calls find median, all we have to do is just return the median that we have. So we're just going to return self.median. That's it. And we'll make sure to return it as a floating point. Cool. That should be it for our solution. So let's submit it. Okay, so small mistake on my side. This is going to be self.left min heap, same for the right min heap. Sorry about that. I made that mistake quite a few places. Over here as well. Yeah, that should be it. So let's try submitting it again. And as you can see, our submission was accepted. So thanks a lot for watching, guys. And do let me know if you have any questions. Thank you.